Hello students, in previous lecture we talk about open spheres and we have taken few examples on open spheres in usual metric space RU, then discrete metric space, okay, and over R2. Construct the open sphere about the origin with radius 1. Now we'll take one more example on open sphere. Let Cu be metric space. Then for z naught is equal to x naught plus I y naught belongs to C, complex number set, and r greater than 0. Open sphere about z naught is equal to set of those z is equal to x plus iy belongs to C such that d of z naught is less than r. Now d of z naught is less than r if and only if mod of z minus z naught is less than r. If and only if what is mod of z minus z naught is nothing but x plus iy minus x naught plus iy naught is less than r. If and only if mod of x minus x naught plus I times y minus y naught is less than r. If and only if under root of, what is definition of modulus of complex number a plus ib, mod z equal to under root of a square plus b square, that is under root imaginary real part square plus imaginary part square. So this is nothing but x minus x naught square plus y minus y naught square is less than r. If I take square, I will get x minus x naught square plus y minus y naught square is less than r square. Okay, and therefore SR Z naught, what is this? This is set of x plus iy. X plus iy belongs to C such that x minus x naught square plus y minus y naught square is less than r square. What is this? This is nothing but interior part of circle, center at origin, center at x naught y naught and radius r. So geometrically, if I have some point z naught here and r is a radius, then if I take any point z here, so this is your S R Z naught. Is it clear? In Argand's plane or in complex plane, with respect to usual metric defined on Cu, we know that mod of z minus z naught is equal to r represent circle with center z naught and radius r. So mod of z minus z naught less than r represent interior part of that circle. Is it clear? So this is nothing but open sphere in complex plane with respect to usual metric. Now our aim is to study neighborhood concept. Neighborhood, okay? So let XD be metric space, XD be a metric space. Then subset n of x, subset n of x is a neighborhood of neighborhood of x belongs to n subset of x. Means it is point from x, but that n, if it is a neighborhood, then it is neighborhood of only point from that set. If there exist r greater than 0, such that SRX is contained in n. SRX is contained in n. So n is said to be neighborhood of its point if you are able to find at least one open square about that x which is completely lies inside x. Okay, that is if there exists open sphere containing x and lying in n. Lying in n. Okay. For example, in RU, first in RU, if I take any open interval, okay, in RU, any open interval is neighborhood of, I use NBHD for neighborhood. Neighborhood of each of its point. Whatever your interval may be. If I take open interval AB, if I take x to be point here, here or here, okay, so then SRX must be contained in AB where R is equal to minimum of mod of x minus a by 2 or mod of b minus x by 2. If I take x to be any point in open interval AB, then if I select R is equal, that x is either near to A, near to B, or it may be center of that AB. Whatever position of that x may be in that interval, depending on its closeness to end point of that interval, if I select R equal to minimum, any open interval AB, if I take here, for this, SRX is containing this, okay? So we'll get that one, okay? Second, if I take open ray also, every open ray is also, okay, any open ray or open ray A infinity is a neighborhood of each of its neighborhood of its any point. Its any point. If I take A and infinity, if I take x to be any point, okay, since if I take SRX is contained in AB, A infinity, where R is equal to mod of x minus A. That x is always near to A rather than infinity. Okay. Similarly, open ray minus infinity to A is neighborhood of each of its point. Each of its point. Is it clear? Third, if I take closed interval AB now, is the neighborhood of each x belongs to open interval AB, but not a neighborhood of A and B. open interval AB is subset of this closed interval AB. So if I take this explanation for showing that open interval is neighborhood of each of its points, so closed set is superset of that. It also contains that open sphere. So closed sphere is neighborhood of each of its interior point. Till I have not talked about the interior point of set, but we'll come across that interior point. But interior is inside point of that set. Okay. Phi A and B are not, or phi this closed interval is not a neighborhood of A and B now. For A, for this endpoint A, even though if I take, okay, but not neighborhood of A and B, as SRA is equal to A minus R2, A plus R is not subset of, and SRB is equal to B minus R to B plus R are not subsets of closed interval AB for any R greater than 0. Whatever choice of your R greater than 0 may be, this A minus R to A plus R contains point less than A, which are on the left side of A, and B minus R to B plus R contain points greater than B, which are not in closed interval AB. That's why closed interval AB is not neighborhood of end points of that closed interval, and it is the neighborhood of each of its interior point, means point lying in open interval AB. Then we'll continue this explanation and we'll see if I take now open sphere, any open sphere, SRX is equal to x minus R to x plus R is the neighborhood of each y belongs to SRX, each y belongs to SRX. On same line again, because it becomes open interval in RU. Is it clear? Then if I take now finite set, any non-empty finite set then if I take countable set, or if n is equal to non-empty finite set or countable set in R, like set of natural number, whole number, integer, rational number, or 1 by n, n, or set of irrational numbers, P is equal to set of irrationals, or any non-empty set not containing open interval, non-empty open interval is not neighborhood of any point of n. If I take n is equal to either an empty finite set, okay, if n is equal to say x1, x2 up to xn as subset of R, then for this x2, if I take open sphere about x2, which becomes x2 minus R to x2 plus R, which is interval is uncountable set. So even though there is some uncountable set, like set of irrationals, which is uncountable, but it doesn't contain any open interval. And open sphere about any point is always open interval. So if I take any subset of R in which there is no any open interval contribution, then that n must not be neighborhood of its any point. I think this must be clear to you now. Okay. So this is about this one. Next example, in discrete metric space, xd, any subset n of x is a neighborhood of each n belongs to n as S half n is singleton to n is contained in n, where d of xx is 0 and d of xy is 1 for x not equal to y. Is it clear? So where discrete metric space is defined like this, then if I take any subset of that discrete metric space, then for any point n in n, if I take the open sphere about n with radius half, we know that open sphere in discrete metric space is either singleton set for r less equal 1 and it is whole set for r greater than 1. So I am taking half here. If I take r equal to 0.9 or 1, in fact it is just singleton set and it is contained in that set. Is it clear? So whatever my choice of n set may be, you can say that empty set is also neighborhood of each of its point. Empty set, note, if xd is metric space, then 1 x is a neighborhood of each of its point. Each x belongs to x. And second, phi is neighborhood of x belongs to phi. X is a neighborhood of each of its point. So if I take any open sphere about x, it is subset of x. By definition. So whole metric space is always neighborhood of each of its point, and phi empty set is neighborhood of every point in it, because there is no any point in phi. Each of is neighborhood of x belongs to phi of each point in phi, as phi contain no element. And that's why if I say that phi is neighborhood of each of its point, that statement is correct. Okay. So this is about the neighborhood concept. Now we'll take the theoretical part. or neighborhood. Okay. One of the most important theorem on neighborhood. So let XD be a metric space. Let XD be a metric space. Then N is a neighborhood of, then subset N is neighborhood of P belongs to N if and only if and only if there exists open sphere, if and only if there exists an open sphere SRX such that P belongs to SRX is contained in N. So firstly we prove, suppose N is neighborhood of P belongs to N. Suppose that is the necessary part. Okay. Suppose N is the neighborhood of P belongs to N. Then by definition of neighborhood, then there exists R greater than 0 such that P belongs to SRP is contained in N. Is contained in N. In this case, X is equal to P is such that P belongs to SRP which is equal to SRX is contained in N. So one way result is proved. Okay. Sufficient part. Conversely, assume that, or suppose for P belongs to M, here assume that N is neighborhood. Now, what is the converse part? For P belongs to N, there exists open sphere. Conversely, suppose for P belongs to N, there exists open sphere SRX such that P is contained in SRX is contained in N. What is claim? N is neighborhood of P. N is neighborhood of P. Case 1. If SRX is equal to SRP, then result hold. Case 2. If SRX is equal to SRP, that is P is equal to X. Okay. If P not equal to X, okay. Then to show there exists some R1 greater than 0 such that P belongs to SR1P is contained in SRX is contained in N. Is contained in N. So I have some N here. This is my X. This is my SRX. This is point P. P is in SRX. Okay. Then this is my R1 distance. R1 distance. Okay. So since P lies in SRX, since P lies in SRX and P not equal to X implies 0 is less than d of XP is less than R. Is less than R. Take R1 is equal to R minus d of XP. Then to show, we'll show that SR1P is subset of SRX. SRX. So let Y belongs to SR1P. If I take any point in Y now, in this, then it lies in SRX. Geometrically you are observing that. Okay. Then d of YP is less than R1 is equal to R minus d of XP, which implies d of XP, this is also same as d of PY by symmetry. D of XP plus d of PY is less than R1. By taking d of XP on this side, we are getting this step. So this is 1. Now, by triangle inequality, we have d of XY is less equal to d of XP plus d of PY is less than R1, which implies d of XY is equal to d of YX is less than sorry, what this will get here, d of this is less than R1. R1 is equal to R minus d of XP. So here R, sorry, R. Is it clear? So d of XY is equal to d of YX is less than R. This implies Y belongs to SRX. Okay. Y is arbitrary point in this. Thus, since Y is arbitrary, therefore Y belongs to SRX for every Y belongs to SR1P, which implies P belongs to SR1P is contained in SRX is contained in N. This implies N is the neighborhood of P. N is neighborhood of P. Is it clear? So thus we have proved very important result about neighborhood. I am stating one exercise for you. Exercise or next theorem. Let Xt be a metric space. Xt be a metric space and X belongs to X. Let Nx be collection of all neighborhoods of X. Then 1 Mn belongs to Nx implies M intersection N must belongs to Nx. And second, N belongs to Nx and M is superset of N implies M belongs to Nx. This is one important result. Okay, so within 5 minutes we'll try to prove this. Proof 1. Since Mn belongs to Nx, implies M and N are neighborhoods of X. Implies there exist R1, R2 greater than 0 such that SR1X is contained in M, SR2X is contained in N. Okay. X belongs to this, X belongs to this. Take R is equal to minimum of R1, R2 greater than 0. Then we'll get SRX is contained in SR1X and SR2X. SRX lies in this. Implies SRX, X belongs to SRX is contained in M intersection M. This is say 2, this is 1. This implies M intersection N is a neighborhood of X and therefore M intersection N belongs to Nx. Remember, union of two neighborhoods must be neighborhood. Union of two neighborhoods is always neighborhood. But intersection of two neighborhoods is a smaller set. And that's why we checked here how that intersection of two neighborhood is a neighborhood. Here also now, if N is neighborhood of N belongs to Nx, that N is neighborhood of X. Okay, second. Since N belongs to Nx, implies N is the neighborhood of and M is superset of N. N is the neighborhood of X. Implies there exists some R greater than 0 such that X is contained in SRX is contained in N is contained in M. So X belongs to this contained in N. This implies M is a neighborhood of X, and therefore M belongs to NX. So whenever we have some neighborhood of given point, then its superset is always the neighborhood. So with this discussion, today we'll stop our lecture. Thank you. We'll meet in next lecture with open set concept. Bye bye.